So, Jai Hind to all of you. I am Sulekha Saxena, Assistant Professor, EC Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, we are going to study an important topic of electronics engineering, which is syllabus of first year BTech students, that is operational amplifier. Operational amplifier is a op-amp with a very high gain differential amplifier. It has high input impedance and low output impedance, and basically it consists of two inputs and one output, and we can say that the output V0 is nothing but gain of differential amplifier with difference of input 1 minus input 2. So basically this amplifier amplifies the difference of these inputs with a gain A to generate output V0. If we can say that the difference of two inputs is Vd, then the output with a capital A gain of amplifier, then output can be written as A multiplied by Vd. Operational amplifier is basically used for mathematical operations. That's why it is called as an operational amplifier, because it can perform all type of mathematical operations. So now we will see how it performs various operations. It is basically an integrated chip, that is IC. So we will see its IC number and various functions. Basically op-amp has a symbol of just a triangle with two inputs and one output terminal. One input is inverting or negative and the other is non-inverting or positive input. The input terminal that is seen by negative sign is called as inverting, whereas the input terminal which is seen with positive sign at 2 is called as non-inverting terminal. This IC uses two DC supply. Maximum positive DC supply is called as V plus or plus VCC, and maximum negative supply is called as V minus or minus VEE. The output is at pin number is at identified here as number 3. This IC comes into two different type of packages. One is 741 op-amp, which is a dual 8-pin dual inline package. It consists of 8 pins and the single op-amp IC. The pin number 2 and 3 are input terminals, 2 as inverting input and 3 as non-inverting input. Pin number 6 is output. Pin number 7 and 4 are plus minus VCC. Pin number 1 and 5 are offset null pins, which are used to nullify any offset error within IC. And pin number 8 is not connected, that is left open pin. This IC also comes in a dual op-amp 1458 pin IC, which is also a 8 pin IC, but it consists of two op-amp with op-amp 1 input 2 and 3 and output at pin number 1, and op-amp 2 with input at 5 and 6 and output at pin number 7. Pin number 8 is plus VCC and pin number 4 is minus VCC. But generally in educational purpose we use 741 IC because it's a commercial grade low cost IC easily available in market. As we can see, this IC consists of two input terminals, and if we ground the negative terminal, then and apply the input at positive terminal. Since the input is at positive terminal and this IC simply amplifies the input, so the output will be in same phase with respect to input. So if negative terminal is grounded and the input is applied at the positive terminal, then there is no difference or 0° phase change between input and output. Similarly, if the positive terminal is grounded and the input is applied at the negative terminal, then output is gain into minus of V in, that is there is a 180° phase shift between input and output. So if positive terminal is grounded and the input is applied at negative terminal, then there is a 180-degree phase change between input and output terminal. Now we move towards the single-ended and double-ended configuration. Single-ended means we ground one of the terminal and apply input to another terminal. So if we apply input to only one terminal, then it is called as single-ended configuration. Previous two configurations are single-ended configurations. So if we apply the input to the positive terminal, input and output are in same phase. Whereas if we apply the input at negative terminal, then the input and output are 180-degree out of phase. Now moving toward differential or double-ended input, if we apply the input between input at both the terminals, then this IC basically amplifies the difference of both the inputs, that is V1 and V2. If we apply V1 and V2 at positive and negative terminals, then difference of input is nothing but V1 minus V2, and this IC amplifies this difference with a gain A, that is V naught equal to A into Vd, that is V1 minus V2, which is quite similar to this application. So the double-ended configuration can be seen as two inputs and two outputs. With input Vi1, output is Vo1. With input Vi2, output is Vo2. And if one of the value is grounded, the output is directly proportional to another input. Now common mode operation, this IC basically operates in two types of operations, that is common mode and differential mode. So we will first of all check what is common mode operation. We will see the word common means if the input to both the terminal is common or same, then it is called as common mode operation. And as we can say that the two inputs are equally amplified and the outputs are in and these two are in opposite polarity. So ideally it results in 0 volt because V naught equal to gain multiplied by V1 minus V2. And if these both the values are same, then it is V1 minus V1, which is equal to 0. So ideally common mode operation, in common mode operation output is 0, and practically a very small output will result because of imbalance in different stages of amplifier. Now moving towards differential configuration or differential amplifier. This circuit is basically a BJT based differential configuration which is internally used in op-amp for different stages. So it consists of two common emitter BJTs with input at base terminal. Emitter is common with a supply grounded or minus VE, and the collector is connected through RC to VCC. So when we apply input at V1 and V2 terminal, the output is nothing but gain of amplifier multiplied by V1 minus V2. So when different inputs are applied to op-amp, the resulting difference signal is Vd equal to Vi1 minus Vi2. And when both the inputs are same, a common signal is generated which is half of, that is average of both the inputs, half of Vi1 plus Vi2. So the output of signal consists of two components, output due to differential signal and output due to common signal. So ideally common mode value is 0 and output is nothing but AD into VD, but practically a small amount of common mode signal exists, and hence overall output of op-amp is nothing but AD-VD plus AC-VC, where AD is differential gain, AC is common mode gain, VD is differential voltage at input of amplifier, and AC is common voltage at input of amplifier. So if opposite polarity inputs are applied to an op-amp, that is one input is V1 and other is minus V1, then the difference of these two inputs will nothing but equal to 2 into Vm, whereas when the common mode value is equal to 0. So the resulting output voltage is nothing but AD into 2Vs, that is twice of differential gain multiplied by twice of input voltage. Whereas when same polarity input are applied to the op-amp, then differential voltage V1 D equal to 0, whereas common mode voltage is Vs, generating output AC into Vs. So this shows that when the same inputs are applied to both the signals, that is common mode signal or in phase signal, then the output is nothing but the common mode gain multiplied by the input signal. So then moving towards the equivalent circuit of an op-amp. An op-amp broadly consists of is an IC, and it broadly consists several BJTs, resistors and capacitors. The overall block diagram of op-amp consists of 4 stages: input stage, differential stage, gain stage and then output stage. The overall functioning is equivalent to a circuit with input impedance Zin, output impedance Zout, both the terminals with input voltage V1 and V2, gain is equal to difference of input, output is equal to difference of input multiplied by gain, that is A into V2 minus V1, and this is passed through output impedance Zout to final output terminal. This IC is powered with plus and minus VCC supply. So op-amp is basically an IC with a very high gain, and it can be used in open loop or closed loop configuration. In open loop configuration, where there is no feedback path from output to input, the gain ideally is infinite and practically in the range of 10 to the power 5. So open loop configuration is practically not possible to be used as for mathematical operations because the gain is very high. So it is not possible to add, subtract, multiply or divide in this range. So basically open loop configuration can be used as waveform generator or comparator only. We will study it later on in this lecture. But first of all, we will see the difference between open loop and closed loop. So when there is no feedback from output to input, it is called as open loop configuration. Open loop configuration has very high gain and hence it cannot be used for any mathematical operations. That's why we need closed loop operation. And to reduce the gain, we use negative feedback. So here negative feedback is used, that is negative terminal of input. Output is connected to the negative terminal of input. Negative feedback reduces gain and make this amplifier feasible for mathematical operations. Negative feedback also improve many characteristics of op-amp, which we will see later in these slides. So this is a very basic example of negative feedback. If the output is connected to the negative terminal of input, then it gives negative feedback. Similarly, if output is connected to positive terminal, then there is positive feedback. So make it an important note that for mathematical operations, always negative feedback is used, that is output is always connected to the negative terminal of input. So if we ground the positive terminal and apply the input to the negative terminal, then it is called as inverting op-amp. We use two resistors, one to apply the input to op-amp and one resistance between output and negative terminal of input as feedback resistance. So here the signal is applied to the inverting terminal non-inverting terminal is grounded. Feedback resistance is used between output and negative input terminal. We can also see here that due to the concept of virtual ground, since the input impedance of this circuit is very high, ideally infinite, so zero current draws through both the terminals and hence there is no voltage drop across this resistance. Thus, these both the terminals are at same voltage. So, if one terminal is directly connected to ground, then the other terminal will also be at ground. That is called as concept of virtual ground. It is a very important concept in op-amp circuits, that if one terminal is ground due to very high input impedance, virtually another terminal will also be at same potential, that is 0 volt, but not actually connected to ground, which is called as virtual ground. So, if positive terminal is ground, then this is also is at 0 volt, and if we apply KCL at this node, we say it as node A, then I1 is equal to I2, because this current is 0. So, applying KCL, we can write here as I1 equal to I2, or we can write V1 minus 0 by R1 is equal to 0 minus V0 by RF. From this, the gain V0 upon V1 is equal to minus RF by R1. So, using this, we can easily derive the gain of this amplifier. And if we put both these resistance equal, RF equal to R1, then the gain of this amplifier will be 1. But there is always a 180-degree phase shift between input and output. Means if we apply a sine wave, then the output phase will be in reverse order. So, now we will see other practical op-amp circuits, that is non-inverting amplifier, unity follower, adder, difference amplifier, integrator and differentiator. We have already seen this circuit, that is inverting op-amp. Here the positive terminal is grounded, input is applied to the negative terminal, that is ground and input. Rn and Rf is used as resistance. Due to concept of virtual ground, both the terminals are at 0 potential, that is if V1 is grounded, then V2 is also at 0 volt, and thus In is equal to If, which gives gain A is equal to minus Rf upon Rn. Previously, we have already derived this. So, we have already done this derivation using current relation, and we see that there is a negative sign which denotes 180-degree phase shift. Now, if the input is applied to the positive terminal, then it is called as non-inverting configuration. So, that is if input is applied at inverting terminal, it is inverting configuration, and if the input is applied at non-inverting terminal, then it is non-inverting configuration. So, in this here example, the input voltage is applied directly to the positive terminal, but feedback, remember feedback is always negative. So, feedback output is connected to the negative terminal, inverting, and then throughout to ground. From voltage divider, we can see here that this voltage V1 is equal to V0 into R2 upon R2 plus Rf. So, V1 is equal to V0 into R2 upon R2 plus Rf. And from the concept of virtual ground, and since this resistance is very high, so these both the terminals are at same voltage. So, V1 is equal to V in, and from here we can derive V0 upon V in is equal to R2 plus Rf upon R2, that is 1 plus RF by R2. So, the gain of non-inverting configuration is 1 plus RF by R2. We can here see this derivation. But as there is no negative sign, so the output and input are in same phase. So, if we apply a sine wave at output also, we will get an amplified value of sine wave. And we can easily adjust the gain of this amplifier by adjusting RF and R2. But this gain can never be adjusted below 1. That is, the minimum gain for non-inverting amplifier is unity. Now, if we make this feedback resistance 0, that is, we directly connect output with input, then the gain will become 1, and then it is called as voltage follower or unity gain buffer or amplifier. So, if we made feedback resistance 0 and R2 infinite, that is, there is no need of input R2 terminal, then the resultant circuit is called as unity gain buffer. That is, that we connect input to the positive terminal and simply apply the feedback line towards input. So, this V out is nothing but equal to V in, that is gain equal to 1. We move towards another example, that is summing amplifier. Summing amplifier is another type of op amp which is used to add multiple inputs to generate single output. So, here we take 3 inputs V1, V2, V3 and apply these values to the negative terminal through resistance Rn, and the feedback resistance is again Rf. We take here the inverting configuration, that is positive is connected to ground, and using the concept of virtual ground, and since Rn is infinite, so the point X is also at 0. Hence, using this circuit we can say that I1 plus I2 plus I3 is nothing but is equal to IF. Since this current is 0, so all these current combined flows to the output terminal. And we can see from here that V1 is nothing but I1 is V1 upon Rn, I2 is V2 upon Rn, I3 is V3 upon Rn, whereas Rf is 0 minus V out by Rf. So, we can say that V naught is equal to minus Rf by Rn V1 plus V2 plus V3. So, this circuit adds all the values at the input. So, we can generate a summing amplifier for n number of inputs by just connecting the number of inputs at inverting terminal, and we can adjust the gain by adjusting the value of Rf and Rn. If all the resistance are equal, then the gain is equal to 1 and V naught simply adds all the inputs with 180-degree phase shift. So, this is the given derivation and the output of summing amplifier. Now, moving toward difference amplifier. Difference amplifier basically generates the difference of both the inputs towards output. Here, as none of the terminal is directly connected to ground, so we cannot say that VB or VA one of these values is 0. So, we will consider these both values as V, since the input impedance is infinite. So, VA equal to VB. So, now we apply the KCL at VA and VB, and I1 equal to IF and I2 equal to I3. So, we can say I2 equal to I3, that is V2 minus V by R2 is equal to V by R4. From here we will calculate V and substitute it in the upper value. So from here we can say that V2 by R2 is equal to V 1 by R4 plus 1 by R2. We will again solve it. V into R2 plus R4 upon R4, as R2 and R2 will be cancelled out. So V can be written here as V2 into R4 upon R2 plus R4. This V value is substituted into the next KCL equation, which states that I1 equal to IF, that is V1 minus V by R1 is equal to V minus V naught by R3. We will again solve this equation and substitute V here. The final value, we substitute this value, and then at the next equation we substitute and get the final value as minus V1 R3 by R1 plus V2 R4 upon R2 plus R4 into R1 plus R3 by R1. We can also continue with the previous derivation. We can here see that V1 minus V by R1 is equal to V minus V naught by R2. So V1 minus V by R1 is equal to V minus V naught by R3, where V is written as V2 into R4 upon R2 plus R4. So V here written as V2 into R4 upon R2 plus R4. So here we will substitute V. First of all, we take V1 and V naught at one side, that is V1 by R1 plus V naught by R3 is equal to V 1 by R1 plus 1 by R3. So we take V1 and V naught at one side and V at the other side. Next we substitute V as V2 R4 upon R2 plus R4, and here R3 plus R1 upon R1 R3. V is also V1 by R1 and V naught by R3 at the other side, and V into 1 by R1 plus 1 by R3 here side. We will solve it, substitute V2, and next we take V2 as V naught at one side and minus V1 by R1 at this side. Next we multiply R3 at both the sides and cut at this side. Now this is the obtained expression, that is minus V1 into R3 by R1 plus V2 into R4 by R2 plus R4 and R1 plus R3 by R1. So we have reached till this point. Next, in this circuit, if both the branch resistance ratio are balanced, then only we can easily generate it as perfect differential, that is R3 by R1 equal to R4 by R2. So the primary condition for this circuit to behave as a differential amplifier is R3 by R1 equal to R4 by R2. So we will substitute here, that is divide both the sides by R2 R4. So it becomes V2 upon 1 plus R2 by R4. Here we divide numerator and numerator by R4, and in this side we divide by R1. So 1 plus R3 by R1. And from previous case we see that R3 by R1 equal to R4 by R2. So, we substitute here R3 by R1 as R4 by R2. So, we can easily see that by solving this, we get minus V1 into R3 by R1 plus V2 into R3 by R1. So, we take both the values common and we get V out as R3 by R1 into V2 minus V1. And if we substitute all the resistance values equal, then this gain will be unity and it is called as unity gain differential amplifier. So, we will stop our discussion till this point. We have covered in this video lecture what is op-amp, what are different type of op-amps available, that is single and dual package, basic op-amp, its working, inverting configuration, non-inverting configuration, summing and difference amplifier. We will continue our discussion in the next video lecture. Thank you.